hello to everybody, and I am very pleased that this time we will continue on the mechanism going from insolation to sedimentary records. And it is, you see, last session was given by Didier Paillard about the formation of ice, essentially, and climate response to insolation. But this time it will be by David de Vleeschouwer, and it will be on the Pre-Cenozoic paleoclimate response to astronomical forcing. David is from the Belgium group. He made his PhD thesis with Philippe Claes and Michel Crucifix, so he benefited from both climate modeling and geological background, which is, I think, a very good background. And then he was a postdoc at Marum with Eiko Palik. And now he has a permanent position in Münster. Permanent position, is it permanent or?
It's a tenure track, so if I don't offend anyone, it should be permanent.
Yeah, so it's stable position in Münster, where he has is starting a group and hopefully raising this group to a bigger level. So David, we are very pleased to hear you now.
So yeah, thanks for the invitation, Jacques. I will share my screen now. So yeah, thanks again, Jacques, for the invitation. I'm gonna talk about the pre-Cenozoic paleoclimate response to astronomical forcing, a little bit a natural continuation of Didier Paillard's talk, which was the previous one. And actually, I'm gonna make the transition very smooth because I'm gonna start my talk on the pre-Cenozoic with the Quaternary ice ages. And I want to emphasize that not even 200 years ago, the Quaternary ice ages were still a complete mystery for our colleagues back then. And two notable colleagues in this respect are Louis Agassiz and Jean de Charpentier, who made first order observations around the Alps, noticing ant moraines and erratic boulders very far away from the present-day glaciers, kilometers, tens of kilometers away from the present-day glaciers. And based on those observations, they hypothesized that there must have been much larger glaciers, even ice caps, ice sheets covering the plains and the mountains of Europe, Asia, North America. And they coined the term ice age. Yet they did not make the link between astronomy and continental ice volume yet. Joseph Adhémar, around the same time, was the first to make the link between astronomy and ice volume. However, in a way that we now know is incorrect. And that is because Adhémar reasoned that the reason why we have so much ice on Antarctica is because the Earth is very far away during southern hemispheric winter in July. So the Earth is in the aphelion in July, and therefore the Earth must be cooling in the southern hemisphere, and therefore we have cold winters in the southern hemisphere, and he attributed the Antarctic ice sheet to this. Of course, we now know that is wrong, yet Joseph Adhémar was the first to connect continental ice volume and precession. Only 20 years later, James Kroll continued in that direction, thinking about the connections between climate and ice and astronomy. And he theorized that changes in the Earth's orbit, and notably precession, could cause a diversion, geographical diversion of the Gulf Stream, bringing less heat into the Arctic, more ice, sea ice in the Arctic, and an enhanced positive albedo feedback mechanism, triggering a feedback loop, putting Earth in an ice age. And we now know that this is indeed a very important process in the Quaternary Earth system, and a process very sensitive to precession forcing, insolation forcing. So you might think, why don't we call the Milankovitch cycles the Kroll cycles then? Well, that unfortunately is because James Kroll was wrong in a very important other aspect, and this has also been covered by Didier Paillard in his talk. And the problem there is that James Kroll theorized that precession induced glacials alternatingly on the northern hemisphere and southern hemisphere. So according to James Kroll, we would have a northern hemisphere ice age when the Earth is in the aphelion during northern hemispheric winter, and we would have a southern hemispheric ice age when the Earth is in the aphelion during southern hemispheric winter. And he already hinted at the influence of eccentricity as well, and you can see that very nicely here in this plot. So you see that he's suggesting these alternating ice ages between the northern hemisphere and the southern hemisphere during eccentricity maxima. And then he notes that in the recent time, in the last 70,000 years, eccentricity was relatively low, making that we don't have this alternation between northern hemispheric ice sheets and southern hemispheric ice sheets. And that's what he calls the interglacial epoch. And the high eccentricity time he calls the glacial epoch. Very nice theory. Unfortunately, it's wrong. And that is why we're not talking about Kroll cycles, but we rather talk about Milankovitch cycles. And note that it took another 80 years from 1864 for the Kroll theory to 1941 for the Milankovitch theory. Milankovitch, who is remarkable for two reasons, I would say. First of all, he was an engineer and a mathematician able to calculate insolation for any given latitude and any given season, everywhere on Earth. And he was not only able to calculate that insolation, he also linked minima in the insolation that is received at the high latitudes during summer. And he linked that minima in insolation during summer. Note that he was the first to link that, or at least of the people I noticed or I mentioned in my previous slide, he was the first who emphasized it was the summer insolation that is the key here for triggering a ice age. We need low summer melt. We need cool summers for ice to survive summer in order to have an ice age. And you see here, indeed, he draws in these black portions here, minima in insolation during summer in high latitudes is the key for Quaternary ice ages. And that is why we call, or that is why the Milankovitch theory sensu stricto refers to the Quaternary glacial interglacial cycles. If we then zoom out from the Quaternary towards the entire Cenozoic, we made an incredible amount of progress over the last, I would say, 3-4 decades in understanding the Earth system response to astronomical forcing before there were two ice caps on our planet. So the Milankovitch theory really refers to a bipolar glaciated world. Well, thanks to scientific ocean drilling, we got benthic oxygen isotope records providing us insight into how the warmer worlds of the Pliocene, Miocene, Oligocene, Eocene, and Paleocene have been responding to astronomical forcing. And I think we did a very good job in describing those different climate states, all with their specific, unique ways of responding to astronomical forcing. And so we can consider this job, at least the description of those Cenozoic climate modes in terms of astronomical forcing. You might say this job has been done, we're ready with that. Of course, there are still many specific open questions, but the general description is completed with the publication of Thomas Westerholt et al., the Cenogrid reference curve. And that leaves the pre-Cenozoic as the new frontier in cyclostratigraphy. So again, I'm zooming out. First, I zoomed out from the Quaternary to the Cenozoic, and now I'm zooming out from the Cenozoic to the entire Phanerozoic with the Cenogrid curve over here, and this going further back in time. And when I'm saying pre-Cenozoic cyclostratigraphy is the new frontier, I'm really seeing three main reasons why that is the case. And the first one is obviously paleogeography. Of course, the Cenozoic climate modes, the different Cenozoic climate modes also have to do with important openings of seaways. I'm thinking about here the Tethyan Seaway, for example, the Drake Passage, the Tasman Gateway, India bumping into Asia. Yes, important tectonic changes, but the scale of tectonic changes over the entire Phanerozoic, that's another ballpark. I mean, here in the late Paleozoic icehouse, we're really talking about a supercontinent, the Pangaea supercontinent. If we're going further back into the Paleozoic, we have all the continents concentrated in the southern hemisphere, and we have a northern hemisphere that is basically completely ocean. Those are really completely different boundary conditions in terms of plate tectonics that we're facing. Second reason why pre-Cenozoic cyclostratigraphy is a new frontier is the amplitude of global average temperature. If you look at the difference between the hothouse of the Cretaceous and the icehouse of the Carboniferous, the amplitude between those two extremes is almost double of the amplitude we have here throughout the Cenozoic. So we have a much higher range of climatic states in terms of temperature over the last 500 million years compared to the last 66 million years. And then the third reason why cyclostratigraphy is in pre-Cenozoic cyclostratigraphy is the new frontier is depicted here in this panel. What I did here in this panel, I'm looking at the difference in phase between 10 different astronomical solutions for eccentricity. More specifically, for the 405,000 year component in eccentricity. And so you see that in the Cenozoic, they're all in phase. So they have a phase difference of 0. They're going up and down together at the pace of the 405,000 year eccentricity cycles. However, starting in the Cretaceous, these different solutions, even for the most stable 405,000 year eccentricity cycle, start to disagree on their phasing. What is the exact time we are in a maxima or in a minima? That means that in the pre-Cenozoic, we don't have a tuning target anymore that astronomers can provide us with. And that makes cyclostratigraphy, of course, a different game, a different, a different job compared to the Cenozoic. And these three challenges are also how I structured my talk a little bit. Now I'm going to talk about paleoclimate, and then later on in the talk, I'm going to talk about using Milankovitch cycles as a metronome rather than a tuning target in the pre-Cenozoic. And then I'm going to conclude with some astronomy, how we as geologists, as cyclostratigraphers, might provide useful constraints for astronomers like Jacques to generate that next generation of astronomical solutions. But as I said, I'm going to start with paleoclimate, understanding state-specific Earth system responses to astronomical forcing throughout the pre-Cenozoic. And I'm going to start with a comparison of the very cold late Paleozoic icehouse here in the Carboniferous. And if I'm saying Carboniferous, you're immediately thinking about the cyclothems, probably. I'll come to that. And I'm going to juxtapose the icehouse here with the late Devonian warmhouse around 375 million years ago. And when you compare both worlds, I think what is noteworthy is that for the late Devonian, we have a relatively straightforward response of the climate system to astronomical forcing. If you look through the literature, the Earth system components that are mentioned to be sensitive to astronomical forcing are monsoons, wildfires, and sea ice mostly. And all three of them work in a relatively rapid and straightforward way. You have more insolation during the wet season over the Euro-American continent. You have an intensified monsoon, more runoff, and more detrital input in your sedimentary records that are typically in your marine sedimentary records that are very well studied here in the Rhino-Bohemian realm and in the Appalachian realm and southern China over here. the picture is very, very different if we look into the Carboniferous world. And that is because there are many different there are many boundary conditions that are completely different. We have a much more complex continental biosphere. We go from very monospecific or monospecies forests in the late Devonian to a much more complex continental biosphere in the Carboniferous, with the expansion of seed plants specifically, and that allow continental vegetation to occupy all different continental niches, higher up or further away from water, higher up in the topography. Apart from that, we have the supercontinent of Pangaea forming, obviously, and we have the growth of large continental ice sheets here on Gondwana. Next to these ice sheets, we have permafrost, and we have also the big coal deposits of the Carboniferous, a lot of organic carbon burial on the continents happening. And all of these components, all of these components I just mentioned, so continental ice, organic carbon burial continent, and permafrost, they have typically a much slower response to astronomical forcing compared to the monsoons and the wildfires of the Devonian. And so increasingly with time, going from the Devonian to the Mississippian, we have an increasing low-pass Earth system response to astronomical forcing, with many more nonlinear components in the system, both in the climate system and in the carbon cycle, and as well in the cryosphere, of course. And despite the significance of those cyclothems, the cyclothems that are typically associated with 100,000 and 400,000 year eccentricity, we are very far away from a full understanding of why the Carboniferous climate system is responding the way it does to astronomical forcing. And to me, it's very analogous to the 100 kiloyear problem that received a lot of attention for the Quaternary. However, we have to come up with a similar explanation or a similar list of nonlinear responses of the Carboniferous Earth system that can explain the cyclothems and the low-pass Earth system response of the Carboniferous Earth system. But for now, for the next couple of slides, I wanna take a step back to the Devonian, because the Devonian is really the period where on which I did my PhD and where I did a lot of work, and where also now Nina Wicheren in my group is doing a PhD. And the specific research question that Nina is evaluating is whether or not Devonian anoxic events were paced by astronomical forcing. So on this slide, you're looking at an excerpt from the Devonian timescale, the most recent one. And here in this column, you see global events, and basically, or roughly speaking, all those global events are periods during the Devonian or intervals during the Devonian where the ocean water at many different sites around the globe became dysoxic, and in many places black organic rich shales were deposited. And if you look at this barcode kind of representation, you might think that there might be some rhythmicity to it. And if we're saying rhythmicity, of course, Milenkovic is always around the corner. So that is why Nina is investigating whether Devonian anoxic events were paced by astronomical forcing. In order to evaluate that research question, we're looking at different sections in the Rhenish Massif in Germany. And one of those sections is the Winsenberg section. It's a road cut, and it exhibits the lower Kellwasser black shale over here, the upper Kellwasser black shale over here. It has the Frenian-Femmenian boundary over here, and it has very nicely expressed centimeter to decimeter lithological alternations between shales, limestones, and marls, and black shales, of course. What Nina did is she sampled the section at centimeter scale resolution, and she used the lithological variability, which is also nicely expressed in the silica over calcium ratio, as the influence of precession. If you have details in how precisely she converted depth, so this lithological column is in the depth domain, to time. So on the right-hand side, we're in the time domain. I invite you to send us an email, and we can give you all the nitty-gritty details, but I will spare you the details here for this talk. The key message here is that we converted this section, which we think is time continuous, from depth to time based on the lithological variability paced by precession. As I already introduced for the Devonian, it's not a surprise. This is something we see all around the world. The Devonian astronomical signature, especially in tropical paleolatitudes, is precession dominated. What we believe is driving those lithological variability is more or less detrital input. So we have more marly and shaly lithologies when there's more detrital input and a higher silica over calcium ratio, and vice versa for more carbonate-rich layers. If you compare the silica over calcium ratio to titanium over aluminium, you see that we have roughly the same patterns, only that titanium over aluminium, we're comparing two detrital elements, is a proxy for, it's a grain size proxy, and it's telling us something about the way the detrital material is transported to our studied site. More aeolian dominated under drier conditions, when we have a low titanium over aluminium ratio, and more riverine transport, wetter climates, when this ratio is high. So that all makes sense, especially on the long scale here, on the scale of the 100 and the 400,000 year eccentricity cycle. Another ratio we used is the potassium over aluminium ratio. It's a proxy that is often used to look at the intensity of chemical weathering with lower ratios pointing towards more intense chemical weathering. Note that the axis is inversed here. So we have stronger weathering here in the blue and weaker weathering in the orange. And you see that on the long 100,000 year timescales, things are in phase. And that also makes sense, right? We have wetter climates with more detrital input and more chemical weathering. That all makes sense. It's easier to weather when there is water available. Remember, on the time scale of 100,000, 400,000 year eccentricity timescales. That is also confirmed by some XRD clay content analysis, where we have the highest kaolinite versus illite ratio here during the part of the record here in the middle, in between the two Kellwassers, where we expect the wettest climates with the strongest chemical weathering. So that all makes sense until we zoom in again to the precession scale. So to the scale of the individual marl limestone couplets or shale limestone couplets. And if you follow here the green the gray lines, you see a shaly layer characterized by high silica and a high titanium over aluminium ratio is characterized by a potassium over aluminium ratio that suggests less weathering. So we have, on the precession scale, we have wetter climates corresponding to less weathering. And we basically have no other, we basically can only speculate about why that is. And my preferred interpretation is that when you have a precession-driven intensification of your monsoonal circulation, then this additional heat, this additional insolation, this additional energy is all put towards intensifying the monsoonal circulation, making it wetter. And because of the latent heat and because of the net negative cloud radiative forcing of more clouds during these wet climates, you actually have lower temperatures. And so what this might represent is that actually during the precession-driven intensification of the monsoons, you have a lower temperature and therefore less efficient chemical weathering. This is my preferred hypothesis. In the paper that Nina is preparing, we mention a few others, for example, sea level and the distance to shore and so on. But I'm not going to go into the details of all of that. I want you now to zoom out again back to the eccentricity timescale, right, where we can subdivide our record in three main intervals: a dry and highly variable lower Kellwasser interval. Then in between the Kellwasser intervals, we have a wet and stable climate with a lot of chemical weathering. And then we hit the upper Kellwasser and the Frenian-Furmanian boundary with dry and highly variable climate conditions again. So how does that fit this astronomical patterns that we observe in Winsenberg? How does that fit in the hypothesis that I phrased in 2017 and that I like to call the eccentricity minimum hypothesis? And what that eccentricity minimum hypothesis is saying, or the way I phrased it in 2017, is that an eccentricity node, a 2.4 million year eccentricity node, so a period of prolonged low eccentricity, is predating the upper Kellwasser event. So the key to this hypothesis is that during a 2.4 million year eccentricity node, the amplitude of the precession cycles is kept low for several 10,000, several 100,000 of years, which means that seasonal extremes are avoided for a very long period of time. And that's why here in this cartoon, we associate long-term eccentricity minimum with intermediate insolation and therefore a low variability summer monsoon, consistent rain and runoff, and the development of thick soils, thick regoliths that built up on the continent as a result of this prolonged stable climate. Of course, the eccentricity node doesn't last forever, and at some point we're going to get out of that 2.4 million year node, and the precession amplitude picks up again, where we then hit a precession maximum. That increased insolation during the wet season enhances the summer monsoon, increased rain and runoff, and the key here is that this high intensity rain erodes the regolith. When it erodes the regolith, there is an enhanced flux of nutrients, mainly phosphorus, towards the shallow oceans, a eutrophication of the oceans, a consumption of oxygen, and the deposition of black shales. And so that, of course, the eccentricity minimum would correspond here to our wet and stable climate in between the two Kellwassers, and that extreme that return of precession seasonality would correspond to the start of the upper Kellwasser event here. One big problem with this hypothesis is that precession causes the exact opposite climate patterns to occur just 10,000 years later. During a precession minimum, we have decreased insolation during the summer monsoon. We have a weak summer monsoon, decreased rain and runoff. And so it's harder to imagine that your regolith can be eroded. And so we can't advocate here a high phosphorus or a high nutrient influx. Therefore, this hypothesis really hinges on the recycling of phosphorus, the recycling of nutrients from the previously deposited black shales in order to allow for the continued black shale deposition. And so to answer the question that is also the title of the slide, the Winsenberg overall fits very well in the eccentricity minimum hypothesis. However, the one thing that is missing from Winsenberg is that we do not observe any obliquity signature at all in Winsenberg, not even during the 2.4 million year eccentricity node. And that obliquity signature has been a key argument here in 2017 to say that that in the interval just before the upper Kellwasser, we had a 2.4 million year eccentricity node, muffling the amplitude of precession and basically only leaving obliquity as the main driver of climate variability. So that is the key message of that Winzenberg paper by Nina, that yes, the Winzenberg data set is corroborating the idea of an orbital prelude to the upper Kellwasser anoxic event. However, that idea, I'm not claiming that idea is newly produced by me. No, that idea has been proposed before, specifically for the ocean anoxic event 2 at the Cenomanian-Turonian boundary by people like Ross Mitchell, Mathieu Martinez, and specifically Sietske Batenburg in 2016, who specifically associated here this node in eccentricity prior to the Bonarelli level or the ocean anoxic event 2 as the possible orbital prelude to this event or this event of ocean anoxia 94 million years ago. And so with that, I'm at the end of my paleoclimate chapter of the talk, and I would like now to tell a little bit about stratigraphy in itself and really reading geological time in the geological record by means of Milankovitch cycles. However, as I told you, based on this panel, we cannot use the astronomical solutions as tuning targets the way people did that for tuning the benthic scientific drilling records, benthic oxygen isotope scientific drilling records of the Cenozoic. We need to do it in another way. We need to use Milankovitch cycles as a metronome rather than as a tuning target. And I'm currently writing a reviewed paper on that topic. And if you go through the literature, if there for the intervals that have a very good, for the pre-Cenozoic intervals that have a good astronomical timescale, basically if you go through the literature, you notice that everything happened through a path of consensus. You need always sections from all around the world to give information, and it's only by putting them all together an integrated stratigraphy at globally distributed sections can be constructed and a consensus can arise. And I have the feeling for the late Devonian, we're slowly converging towards that path of consensus. And to illustrate that, I want to give you the example of the amount of time that sits in between the onset of the lower Kellwasser event with a positive isotope excursion and the onset of the upper Kellwasser event. Nina determined about 900,000 years for Winzenberg, which is a little bit longer, but consistent with other estimates. I had 600, 700, there was 500,000 by Whalen et al. 450, 670. Only here, this one by Ma et al. Is a little bit longer, but basically in this slide, I don't want to focus here on the details and why there might be 100,000 year more in the one or in the other. I think if we're talking about Paleozoic and pre-Cenozoic in general, but specifically Paleozoic cyclostratigraphy, I think it's important that we work towards a cyclostratigraphic framework where we fit the stratigraphy within 405 kiloyear zones. Fritz Hilgen likes to call those astrochronozones, right? That we fit the stratigraphy into some kind of astrochronological zones, very much like biozones in biostratigraphy, where that can tell us something about cyclostratigraphic correlation and time at the same time. And if you do that, I think we see a very nice path of consensus for the late Devonian, where different authors, Da Silva, myself, Mike Whalen, Lou et al., and now Nina, interpret the Kellwasser crisis here to occur in mainly 3 405,000 year eccentricity cycles, with the lower Kellwasser cycle occurring in what I like to call cycle 15 Then there's one 405,000 year cycle in between the two Kelwasser events. I like to call it cycle 16. And the upper Kelwasser event occurs in cycle 17. Only Ma et al. Has two 405 kiloyear cycles in between the two Kelwasser events. So he has two cycles here. So that is something that we need to figure out what is going on there and how it can be explained before we can reach really this consensus. But that this consensus is important, I want to illustrate here by two other examples. Now I take you to the Cenozoic-Mesozoic boundary around 66 million years, and at the same time to the Mesozoic-Paleozoic boundary around 250 million years. And I'm going to start here with the Maastrichtian, the Cretaceous example, a cyclostratigraphy constructed by Sietske-Batenberg based on the Zumaya coastal section, and you clearly see the three last 405,000 year cycles of the Cretaceous, and Sietske called those cycle 1, 2, and 3. And in the upper panel, you see the 405,000 year cycles, 405,000 year cycles in the different astronomical solutions. And you see they're still all agreeing on the phasing. They're still in phase, going up and down together. And those numbers, that is what Fritz Hilgen likes to call the astrochronozones. So you're basically counting backwards in geological time the amount of, for the number of 405,000 year cycles. And so here, I think everyone will agree that the Paleogene Cretaceous boundary occurs within cycle 164, or within astrochronozone 164. And then cycle 2 corresponds to, cycle 2 in the stratigraphy corresponds to cycle 165 in the solution, and cycle 3 to cycle 166 in the solution. The same path of consensus has been done by Minsong Li for the Meishan GSSP section in China. There was also some controversy about the amount of time contained by different Permian-Triassic boundary sections, and Minsong basically settled this debate by publishing this paper in 2016, where he clearly identifies three 405,000 year eccentricity cycles with the boundary sitting in E0. But the big difference with the Cretaceous example, of course, is that here, if you compare the different astronomical solutions for 405,000 year eccentricity, you see they're completely out of phase. And depending on which one you take, you might associate this cycle E0 in the stratigraphy with either astrochronozone 623 or 624 in the solution. And I think there is a very important task for us as the pre-Cenozoic cyclostratigraphic community, is to really adopt this concept of the astrochronozone and to concatenate those astrochronozones throughout the Cretaceous, throughout the Jurassic, into the Triassic, in a time continuous way, in order to determine from the geological record itself in a very precise and accurate way. And I realize this is going to take years, maybe decades, in order to determine whether the Mesozoic-Paleozoic boundary, the cycle E0, was indeed in 623 or 624. And that way we can work our way really to a much more consistent and cyclostratigraphically constrained coherent geological timescale that is fully connected to the present. And that is, of course, very hardcore stratigraphy, right? And that might not be the most sexy topic on Earth, but it's an important job, though. It's because it's much more than just stratigraphy. And to illustrate that point, I take you to the Triassic-Jurassic boundary, the end-Triassic Delta 13C excursion from Austria and from the Italian Alps. The astrochronology for that has been published by Micharoul et al. In 2011. And here you see two of their sections that that they calibrated against relative time. And so you see a very rapid negative isotope excursion in the organic matter. And that negative isotope excursion has been interpreted as a rapid injection of isotopically negative carbon, probably from methane or from whatever source, an isotopically negative source, into the atmosphere. That sounds familiar because that is exactly what we're doing right now by driving cars and flying planes. We're burning organic matter, and therefore we're injecting isotopically negative carbon into the atmosphere. If you're using an Earth system model to simulate the Anthropocene projection, and a model that allows for isotopes, then what you see is that if we run a scenario in which we peak at 800 ppm CO2 in the year 2150, then we would have a isotope excursion in the surface ocean, so the dissolved inorganic carbon in the surface ocean, with an amplitude of about 4 per mil, exactly the same amplitude as the Triassic excursion, but with a much faster return to equilibrium values, or with a return to stability. So what is that telling us? That is telling us that the projection is missing a big part of the story, because the Triassic isotope excursion is maybe not a perfect analog, but it tells us that in the real world, there are a lot of positive feedback loops and additional mechanisms that are triggered by the initial perturbation that here the Anthropocene projection, this simulation, is not getting. It's probably missing a few feedback mechanisms that are not implemented in the model, and that will hamper, or that will prevent, the signature to go back to equilibrium after already a few thousand years. And instead, if we look at the geological record, we have to anticipate a perturbation of the global carbon cycle of several 10,000s of years, so an order of magnitude longer. So Paleozoic events are not perfect analogs, but these kind of comparisons, for which you need a very good stratigraphy, nevertheless can be informative. And so with that, with that plea for the need, or this argument why we need a good stratigraphy in the pre-Cenozoic, I want to conclude this cyclostratigraphic chapter of the presentation, and I want to go towards astronomy, right? I want to tell a few words about how we can use the geological record to reconstruct the dynamics of the Earth-Moon system, but as well of the entire solar system as a whole. And so I'm gonna, the different arrows here in the slide illustrate that I'm gonna talk about basically every time slice in Earth history, from the Cenozoic, the Mesozoic, the Paleozoic, and the Pre-Cambrian. But first things first, when I'm saying reconstructing the dynamics of the solar system, what do I really mean? Well, I think it's important to understand is that when eccentricity, obliquity, or precession of the Earth is changing, that is all because of gravitational effects of all different objects in our solar system, mainly the different planets in our solar system. And the way astronomers calculate their astronomical configurations back into geological time is by using the motions of the orbits of those different planets. And they are described basically in G terms and S terms, or S frequencies and G frequencies. And basically for every planet, the S frequency refers to the frequency with which the orbital plane of that specific planet is changing its tilt, or the angle with the plane of Jupiter. Jupiter is taken as the reference plane, and the S frequency is basically the frequency with which another planet the orbit of the other planet is doing this motion. And then the G frequency is the rotational frequency of the major axis in the elliptical plane, like the dancing orbits you see here. The frequency of this little dance that you see here, that is referring to the G frequencies. And so these G frequencies and S frequencies, they combine to make obliquity, precession cycles, and eccentricity cycles on Earth. And my personal interest in reconstructing those G terms and S terms was triggered recently, actually, only maybe 2 years ago, by an exceptional Eocene sedimentary archive from IUDP drilling with an excellent signal-to-noise ratio and an excellent time resolution of less than 1,000 years. And so you see here, XRF-derived calcium over iron ratio with individual cycles related to precession. We also had high-resolution oxygen and carbon benthic isotope records. And based on the orbital imprint in those different records, we were able to extract the different individual precession components. For example, we used the calcium over iron ratio, and here this is some kind of a power spectrum. You need to read it like a power spectrum, and we identified the different precession terms. And here you see the G terms popping up: G1, G2, G1 related to Mercury, G2 related to Venus, G3 related to Earth, and so on. And so we extract precession components, obliquity components, eccentricity components from the calcium iron precession envelope, and 4,500 year eccentricity component from delta 18O in a similar way as Paul Olsen did in his PNAS paper. I don't know which year, sorry, Paul. The geological orrery paper.
2019.
2019, thank you very much. We also analyzed it with the time-opt MCMC method and obtained basically the same results or very similar results. And you see those plotted here. So here the red intervals here show us our estimate, or the diamond is the estimate, and the bar is the uncertainty on G1, G2, G3, G4 at 41 million years ago. And you see, for some we agree with the Lascar model, but this is a smoothed line actually. And G3 we suggest a significantly lower frequency compared to what is in this smoothed version of the Lascar 2004 solution. This has major implications, but I'm not gonna expand on those here. What I want to emphasize here is that we can also use this technique to reconstruct the tidal drag of the Earth, that the Earth is experiencing by the tides working on the tides working on the Earth, exerting some friction and slowing down the rotation of the Earth. That has implications for the precession constant P. And you see here that we have very high uncertainty here on our reconstruction of P. Basically, we're in agreement with all different theoretical models, the Waldheim model, the recent Farhat model, the Lascar model. But if we compare our results with other results, for example, the one from Myers and Malinverno right here, and the ones here for the more recent time, for the Neogene time, I think that the data, from the data perspective, what is becoming quite clear is that we have a quite constant precession constant throughout the Paleogene, and then an increase in tidal dissipation, and therefore a more rapid decrease in precession constant throughout the Neogene, right? So slow tidal dissipation throughout the Paleogene, and then a strong increase during the Neogene, probably not unrelated to the continental ice volume that significantly increased throughout the late Paleogene and the Neogene. Then if we zoom out again, right? We zoom out again from the Cenozoic to the entire Phanerozoic, or Paleozoic timescales, as I call it here. Where this plot is very similar to the previous one, only that there is much more time here on the x-axis. We're still looking at the precession constant on the y-axis. Now, the purple line is the new Farhat model made by Mohammed for the evolution of the Earth-Moon system and the precession constant throughout the Earth history, basically. And what Mohammed found was that there are rapid variations in precession constant, right? We have here a rapid decrease in the precession constant, so a lot of tidal drag, and then here throughout the Silurian, Devonian, and Carboniferous, it seems that precession constant didn't change much, but so that implies that there was very little tidal drag and then an increase again. So these rapid variations that come out of the Farhat model need to be ground truthted, of course, by geological data. But until recently, we only had the red, the blue, and the green dots available. And basically, there was a big data gap here in the Devonian, and that has now been filled by Christian Zieden in a paper that is now in press with EPSL. He constructed here this data point, which seems to suggest that the Farhat model seems to corroborate the Farhat model with relatively high value for the precession constant at the Devonian. And now I'm going to zoom out even further. So now the entire Phanerozoic, oops, I've lost my mouse. Ah, here it is. Now the entire Phanerozoic is right here, and here on the x-axis we have the entire, or we have the last 3.4 billion years. And so on pre-Cambrian timescales, of course, we need geological data to basically just differentiate and ground truth different theoretical models, which are the different lines A, B, C, D, E, F. Those are the different theoretical models that exist. This is a figure from Margriet Lantik et al. In 2021, who focused on the Joffre data set. But I want to hijack here Margriet's figure for a second, because I want to zoom in for the end of my talk on the Moody's group here. And so this data point that you see here has been based on an outcrop of a dune, a subaqueous dune from the Moody's group in South Africa, which is the oldest and well-preserved siliciclastic tidal deposit on Earth. And based on those tidal rhythmites, these sedimentologists that published this data point inferred an Earth-Moon distance. But now this same Moody's group has been drilled by ICDP, the International Continental Drilling Program, and we now have 5 kilometers of core throughout this tremendous siliciclastic deposit, 3.3 billion years, that has rhythmic sedimentation, not only on the millimeter and centimeter scale, like these tidal deposits that have been studied for the previous data point, but we can also discern in the cores rhythmic sedimentation on depth scales of several tens of centimeters, meters, several tens of meters, which has the potential to look for Milankovitch cycles, precession, obliquity, eccentricity cycles in those super old cores, which from Mohammed's experience provides a better, usually those data points from cyclostratigraphy or the reconstruction of Earth-Moon dynamics from cyclostratigraphy are in better agreement with the models compared to these tidal rhythmites. Seems to be more robust. So I got involved in this ICDP-based drilling project, and the cores have been drilled last year, and they are now ready to be investigated. So I put in a proposal to the German Research Foundation to ask for money to investigate whether or not there is a Milankovitch signature on the meter scale. And this figure was a proof of concept from this proposal, where in a specific site that has been drilled and for which we had downhole logging data. So here on the y-axis, we have gamma radiation measured during downhole logging over several hundreds of meters of borehole. And according to my very preliminary and probably wrong analysis, There might be precession-scale variability at depth scales of around 4 meters periodicity, and eccentricity cycles would have a thickness of about 25-30 meters. And so now we're in the process of data gathering and ground truthing those downhole logging records. So here we have a natural gamma radiation in black and gray. But of course, we don't know yet what is driving that gamma radiation signal. And just a few weeks ago, together with a bachelor student from Münster, Simone Kuppers, we went to Berlin, where the cores are stored, and we measured at regular intervals the geochemistry of the cores with a portable XRF device. And of course, this is all very preliminary, but if you plot the potassium record against the natural gamma radiation record in the depth domain, you see that the gamma radiation signal is primarily driven by potassium and therefore by clay content. So this is really the signal is really in the clay versus sand, the grain size fraction, and so the rhythmicity here is a grain size rhythmicity, which is very promising. To know that this natural gamma radiation signal is not driven by uranium, for example, but instead by clay versus sand. So clay, high potassium, sand, low potassium. And so in the next couple of years, the German Science Foundation is providing the means to go to the nitty-gritty of all that, to figure that out, whether those are indeed precession cycles and whether we can reconstruct the precession constant for 3.3 billion years ago using those data, because those cores are really fantastic. And with that outlook, I want to thank you for your attention. I hope I was able to convince you that the Pre-Cenozoic is very interesting in terms of paleoclimate states, different paleoclimate states under very, very different boundary conditions. Stratigraphy is important. As a metronome, the concept of the astrocronozone is something I'm very much convinced of, and has its importance to also use pre-Cenozoic environmental records as potential analogs for important Earth processes that we are experiencing today. Think about the Triassic-Jurassic carbon isotope excursion. And then I hope you're all as excited as I am about using these very old rocks, these 3.3 billion year siliciclastic sequences for maybe better reconstructing Earth-Moon dynamics in the deep past. Thank you for your attention.
Thank you, David. Thanks a lot for this overview. And I don't think you have to push very hard to convince us of the importance of the pre-Cenozoic sequences. Looking to the audience that is here, I think they are pretty much already convinced. It's not
it's like preaching the choir.
Yeah. I may ask you or make us first some comment about the 4-5 cycle. Of course, and this it has been quite clear that beyond a certain time, beyond 250 million years, for example, it's pretty much out of phase, and it will remain about whatever is going on, even if we have some improvement on that. But the idea from the beginning is that it is still very interesting to use this cycle as a reference, because they are the same. It's like the paleomagnetic reversal. They are the same all over the globe. So you can use them and basically assume that the period is 4 or 5 kilo year, and that gives you you search locally the cycle, as you mentioned, and of course the importance is to put all the pieces together to be able to say which cycle they are. But these cycles are here and they are present all over the world, and they are numbered. You should So the problem is to know where you are in these numbers.
No, I agree, and this is exactly the concept of the astrochronozone, which all will have an assigned duration of 405,000 years. Very much like the biostratigraphers did a few decades ago. In the Devonian, at least, they assigned all the conodont biostratigraphic zones 500,000 year duration. Of course, they don't have a mechanistic a reason to do that. And no, this is absolutely the way forward.
And if you compare with the, of course, if you have some tie point somewhere where some absolute measure, like some very precise uranium-lead measure is better than the uncertainty on the 4 or 5 thousand year cycle, then you may be able to reevaluate the periodicity. But I think that up to now, it is the accuracy of uranium-lead is still somewhat under what we can reach directly by assuming for just 4 or 5 strict period and using basically a cosine function to make the scaling. And before I give the microphone to Linda, just a small comment on what you spoke about the variability of the G3 frequency. Of course, in the evaluation of the frequency in LA 2004, the average was made basically over 15 million years. So, so there may be, you may, while you are making your geological analysis, you look over a much shorter time. So there may be some issue on either point, but it may also be that it is just a problem of over which time you make the averaging and.
I agree. It's not a fair comparison here. Where I'm basically comparing apples and oranges here with.
Not really. It's still, but it has to be checked whether what is the variability at a shorter time scale and to see whether there is some disagreement or not. Or
because the red data point here is the average of a 2 million year long record, whereas this curve has been smoothed with a
much longer.
If I understand it, with a sliding window of several tens of millions of years. So
probably 15 or 20 million years.
Yeah, exactly.
20 million years for the inner planet.
So that explains.
That could explain, but we can check. Okay, now Linda.
So David, that's an excellent talk. Thank you so much. Really great, every aspect. So you are now an expert on the Cenozoic, and so having worked there now for a decade, perhaps, and so my question, if you look at all the astronomical solutions for orbital eccentricity, for example, of course, we see that they all agree really well within, a few thousand years, all the way out to 40 or 50 million years ago. And you're already saying here in this slide that already we're having a change, a disagreement at 40 million years in this particular with LA 2004, which I think we would have expected. But for everything, say, from today back to 40 million years or 35 million years, how secure are you in, all of the orbital solutions agree. How secure are you in the data itself, in the geological data, that they agree with all of the astronomical solutions? Where are the weak spots? Where are the strong spots? Strong intervals versus weak intervals in your sense of the agreement between geology and model.
What I cannot do in my answer is like tell you or fingerprint a time in the Neogene where where the data starts to disagree with the insolation curves. Therefore, I have to look. But in order to answer your questions, I think we have to look at the precession obliquity interferences.
I'm talking about the orbital eccentricity only.
The eccentricity only. Yeah, then it's really a question of the grand cycles, right? Because here G3 minus G4, that would be the 2.4 million year cycle. When are they starting to disagree? I mean, that's a very difficult question.
I mean, but we have enough data so that an evaluation could be made of the entire orbital eccentricity solution versus the entire eccentricity band of the geological data. Do you think? I mean, are there intervals of time that are still very uncertain?
In the Cenozoic?
Yeah.
I think the most tricky part for making an astrochronology was indeed the middle Eocene, was indeed exactly this interval I pointed at, and we made a lot of good progress with Cenogrid, with I think it's Walvis Ridge that Thomas Westerholt resampled, and I think we now have there since 2020 we figured out the stratigraphy in there, and we are now at a point indeed where we can evaluate whether the good agreement in the solutions is also in agreement with the data. I don't think anyone has really done that on this Cenozoic time scales, really on the composite record. Should be done.
Right. I think it's the last part of, to close the circle. I think that's something that could be done theoretically in a straightforward way.
Yeah.
So that was one of my big questions, because
it's a low-hanging fruit, actually.
Yeah. Well, thank you. That was the main thing. I have a lot of other things to talk about, but that can wait.
Thank you.
Margaret?
Yeah, hi.
Hey, Margaret.
Thanks for the very exciting talk. I learned a lot, and very motivating. Yeah, a couple of questions. So first of all, for the Moody score, is there any chance you can get some independent Uranium-lead ages out of it?
Yes, we did. There are some tough layers, and there are some uranium-lead geochronologists involved, so they will for sure they will try. They already tried, of course, on equivalent layers in outcrops, but the zircons were just not good enough. So we might have hope that the ones from the diurnal cores are less affected by by weathering, and are less affected by that. So yes, there is the hope that this Moody's group will also yield some very high precision uranium-lead ages. But of course, you realize that the diameter of a core is very limited. Therefore, you need to be lucky to have at least a few zircons in there to be datable. I'm not an expert in the field, but it's one of the main targets of the Moody's, and it's also something I badly need for my cyclostratigraphic interpretation, or I mean to ground truth, because here what I showed, I'm only working with the ratios between different peaks in the power spectrum, different rhythmical components, and I can use tests like time-opt or something like that. But if I can use uranium-lead, high precision uranium-lead ages to say something about average sedimentation rates that are consistent between uranium-lead geochronology and cyclostratigraphy, that would be, of course, a major argument to convince the critics that indeed Milankovitch was forcing these siliciclastic, very shallow marine environments, because of course many people will claim that the cycles I see, even when they're there, they might be autocyclic. right? I mean, we're really in a delta system. So one of the key points here in the science there is to convince the non-believers that these are allocyclic patterns and not an autocyclic pattern.
Okay, yeah. Another question. So about at the beginning, you described the sort of the difference between the Devonian climate system response to longitude forcing versus that of the Carboniferous, and then you were saying that for the Devonian it's straightforward, so you see a more direct response, and then in the Carboniferous you see a slower nonlinear response. I think because you see more eccentricity.
Yeah.
So my question is, so how sure are you about this, since we don't really have a global pelagic oxygen and carbon isotope record for those times? So what is the effect of just the sedimentary sections that are preserved and that people have looked at, and what is their latitude? I mean, the fraction that how that preserved, how much is that maybe biasing our view of the response of those systems?
Very, very good question, because everything we know about the response of the Devonian and Carboniferous Earth system to astronomical forcing comes from Europe, US, China, and they were both in the Devonian and in the Carboniferous. They were low to mid latitudes. We have actually very or absolutely no constraints except from climate simulations, numerical simulations, what is going on at the high latitudes. And we know that from the present day that the response of the climate of regional climate to astronomical forcing might be very different in the tropics compared to the high latitudes. So yes, to answer your question, of course there are biases. And the main bias I see is a latitudinal bias, with all the data points being in the subtropics and in the tropics. That being said, that same bias exists between the Devonian and the Carboniferous, and in the same regions. For example, in Belgium we have nice Devonian and we have and very extensive Carboniferous. It's very clear that that there is some kind of a low pass filter and that built into the Carboniferous climate system, making the Carboniferous climate system much more sensitive to those long cycles, right? Compared to the Devonian, where I spend a lot of time on the Winsenberg quarry, which is a perfect example of that really instantaneous response of the monsoon system to the local insolation forcing dominated by precession. Those kind of patterns are much less dominant in the Carboniferous, and in the Carboniferous we see really those cycles between coal deposits and then more marine facies, so terrestrial coal deposits, and then marine facies on timescales of several hundred thousands of years, so much longer timescales. And so I think that is a true difference between the Devonian and the Carboniferous, unaffected by. I mean, this is true. Of course, this is true for the tropical and subtropical latitudes. What's going on at higher latitudes is very difficult to tell. I hope that answered your question.
Yeah, and our final question about this lithological column, I think. The Hinsenberg, I guess. Yeah. The work by Nina. I was just curious. So, would you agree that, because if I look at the middle, the cold interval, or dry, I don't recall, or wet, I think. So that the expression of, in particular, the 405 interpreted 405 kiloyear cycle lithological expression is not straightforward, right? Because you see, in one point you see it's your filtered maximum occurs where you have more of the darker layers, and then the other one you have this. You see that this sort of mottled lithology. So I was just wondering also in that respect, because in the next couple of slides further you showed like the different clay proxies and that they were out of phase in some instances.
Yeah, this one. Yeah.
Whether have you considered also non-melancholic influences in that could explain that, or maybe like the issue of how it's called, close sum effect. So if you add new lithologies, that could maybe affect, explain anti-phase versus in-phase behavior of these different clay elemental ratios.
Yes. I'll start with your first question. I agree with you. If you are on the field, I agree. It's very hard to put your finger on the eccentricity cycle. Whereas that's why here in the pictures and the field pictures we show the decimeter scale cycles that are precession related, but it's very in the field. It's very hard to discern eccentricity cycles, even the 100,000 year ones visually. You only start to see them when you look at the amplitude of the precession filter here, and when you look at the lower variability in titanium, aluminium, potassium, aluminium. The black lines here, they are just running averages. They are not a specific filter or anything. So they can also. I mean, we're not claiming that those are the 400,000 year cycles. This is a combination of red noise, so just climate drift, and the eccentricity forcing, of course. And did we consider the effect of the closed sum effect? It's a tricky one. I have to think about that a little bit with Nina. I can't answer that straight away.
Okay. Well,
thank you.
Thanks.
Okay, so Alberto, you have been waiting for a long time.
No, thanks, David. It was a wonderful talk, and there's a lot of food for thought there, and I'm really happy I could listen to it. I have a very simple comment about your gamma ray comparison, and I apologize if you know this already, but it may be useful to many people in the audience, the comment. So it's where you're comparing the XRF result, right, to the log. So I don't know which was the logging tool that was used in this case, but generally the vertical resolution of those logging tools is much less than the resolution of your XRF measurement. So, for example, the ones I'm familiar with, I think the resolution of the tool is tens of centimeters, something like 30, 40 centimeters or so. So they're averaging essentially the gamma ray response of the formation over that, while of course your XRF would be much more detailed. So my suggestion would be to just do some kind of averaging corresponding to the vertical resolution before you actually make a comparison between the two data sets. And I think that would let you, and you can kind of see that there are the bigger fluctuations in your K2O from the XRF as one would expect. So that's all. Thank you.
No, I agree. And you're right. The way it works is it's pulled up the tool is pulled up in a continuous way, and then it's just measuring continuously, and then just I think every 2 seconds or so it integrates over the amount of stratigraphy it has traveled, which is typically it's typically like 10 centimeters or something like that.
There's a difference between the sampling interval, right? So you may get every 10 centimeters, but the resolution may be less than that. So it's smoothing basically everything.
Yeah, I agree. Yeah, no, very good comment. Thank you.
Okay, any other question in the audience?
Yes.
Paul.
Thanks again for a really interesting talk. I really appreciate it. I wanted to comment briefly, unsurprisingly, on the Triassic-Jurassic transition. There is basically no resolution in the Austrian sections to resolve actually perhaps any orbital cyclicity. There are real problems with the Austrian sections, especially at Kuyak, where there are faults through the section, and this was something that has been pointed out by quite a number of people. But the section is fundamentally acyclical in those Austrian sections, and it's posed a huge problem since one of those, Kuyak, is now the GSSP. There's a move afoot to change that, to change the GSSP, because you can do that every decade or so if you get the votes. The votes were very strongly biased by Ammonite people because that section has good ammonites in it. Well, it has ammonites in it, let's say. Good is a value judgment. I don't think that we have the resolution in time to make a comparison with a model curve. I also think that the origin of that isotopic shift itself is up for debate. I had some papers with Callum Fox and Jessica Whiteside, which show that in, for example, St. Audrey's, where this is St. Audrey's Bay in the UK, where it's usually compared to, the isotopic excursion is driven by a change in the kind of organic matter that is preserved in the sediments, and that what's identified as the initial excursion may be an artifact, a strong artifact of environmental change. But that all has to be worked out. I'm not saying necessarily anything is absolutely right or absolutely wrong, but we, of course, spin the story in the papers. But what's missing for the Triassic-Jurassic are really good pelagic sequences. Now, this Japan, but you really need to get away from the environmental changes that are occurring near the coast. And as you know, when you try to assess cyclicity through one of these huge global events, the proxy record itself is really modified by the environmental changes themselves, even for KT and pelagic records, and it gets to be challenging to identify what the astronomical signal is versus that immense hammer of the environmental change that's going on. I would argue it's entirely possible, for example, in the end Triassic, that the CO2 changes were completely commensurate with anthropogenic change. Dennis Kent and I are working on a paper that shows that the effusive rates of the Central Atlantic magmatic province were extremely high, so that the CO2 could have doubled in hundreds of years. And then had another event not too long after that. But Kuyak and the Austrian sections are without a doubt not the place to do this.
Thanks for the warning.
It's really problematic. There's a paper coming out shortly that basically says the Kuyak section's got to go. It's upside down. There are multiple faults through it. You can't even make a section through it. Just physically, you can't actually measure a section through it because of the faults. You don't know how to put it together. So it violates our principal assumption of thickness being a proxy of time. But the approach is great. I mean, the idea of using the ancient record as an analog for the present when actually the time parts of it are actually similar.
Yeah, I'll probably have to find another record then for making this example, and or maybe a different time interval with more pelagic or
right. Now that's a problem. I mean,
yeah.
the only one I know of that's really pelagic are the Japanese chert sequences. They have other problems, but they are pelagic for sure. And there are other places in the world you could get pelagic sections that compare, but it has yet to be done. Anyway, thanks very much.
Thanks for the warning, Paul.
Okay, thanks. You have any comment on Paul's warning? No,
I just want to thank him for preventing me to run into the knife when I might submit this.
Yes. So this gave Matthias the time to think of something to ask.
No, thanks, David. Of course, I'm quite familiar with most of the things you're saying. I just want to come back to the time estimations of different studies between the Kelwassers, right? I agree. Things are evolving very well in the Paleozoic, and everywhere we're making huge improvements. But if I played advocate's devil or devil's advocate, 400,000, 900, and 1,300,000 years, I can fit 1, 2, or 3 400,000 year cycles, right? And this is what we everywhere in the Paleozoic will see happening in the next years, right? We'll have hopefully different overlapping studies. They will be sometimes very similar, sometimes very different. So I just wanted your 2 cents on how to deal with this, because it's not so easy to actually integrate all these things and correlate. And
yeah, so the point of this slide is that now we have 1, 2, 3, 4, 5 studies that all have one cycle in between the Kelwasser and then another one interpreting 2. My 2 cents in this regarding your question is, it's super important that everyone puts his data in a repository for allowing the check of consistency and maybe even reinterpretation of of most records or of the outlier. I mean, we have to acknowledge that we publish proxy data and then we interpret that in terms of time, but we might as well be wrong about some aspects of it, and therefore it's important that that in order to go the path of consensus, also things can be revised in later work. And so I think the Devonian community is super nice and super open and collaborative, and in this case there is no problem in sharing data. So that's really it's really a nice community. Of course, it might be different in different portions of the geological column where things get a little bit more heated. But my 2 cents to this is, well, it's not because it's published. It's not because it's published is true. So please, whenever you do a cyclostratigraphic study, put your data set on Zenodo, on Pangea, in the supplements, I don't care, but somewhere where people can get to it, because reinterpretation will be part of path of consensus.
And when you are a referee, ask for the publication of the data.
Yeah.
Linda. Oh, you need to put your microphone on, Linda.
I just wanted to chime in to say that, you know, for example, the Ma et al. Paper resampled the same section that you analyzed, you know, 5 years before. And so if you have higher resolution data, I mean, that's really the key to interpretation. So that's how we arrived at twice the time that you did, because of this difference. And there was something else I was going to say as well. We have to work hand in hand with geochronologists, at every step of the way. And, some of our tools, especially for cores, for the gamma ray tool, the spectral gamma tool, it's going to be really great tool to identify potential little tiny ashes, in any given section or any given core that we wouldn't normally see. So, and that also, I encourage people to use the tool to see if they can identify targets for geochronologists to go after. There were other things I was going to say, but those are the two things that, higher resolution sampling is better because if you do too low sampling, you can aliasing is one problem, but also some of the cyclicity can start to look like another band. And so, the Milankovitch cycles, they have this sort of quasi-fractal property about them. So you can mistake, a 400, a eccentricity signal for a precession signal. That has been done by yours truly in the Middle Triassic. And so, it took me 20 years to get higher resolution data to understand what I had done in the Latimar. And we had to actually go to a pelagic section, as you're advocating. We need to do that also further up in the Triassic. So those are all things that, everything is moving in the right direction. Everything is moving towards higher resolution. Just, cores are really the best, but they don't have to be the only way that we do cyclostratigraphy, because we have much better tools now than even 10 years ago. So that's all I wanted to say. I wanted to chime in. So again, thanks so much, David.
Yeah, thank you, Linda.
Okay. I have another question, which is coming back to the 4-5 cycle, 1,000-year cycle. You say that now, over the Cenozoic, is it true that everybody agrees to the relation of the cycle with geology, with the all cycle are identified somewhere in the world and follow in a sequence? There are no more missing cycle. Is that?
I think at least at the eccentricity scale, that is. That's
I'm
fair
thinking
to
of
say.
the 4-5,000-year cycle.
I think everyone now agrees that that goes back to Sietske's. I have to skip a few slides, but that goes back to Sietske's work here. Where is it here? I think now everyone agrees that the KT boundary is in astro-chronozone 164, and so that there are 163 cycles in the Cenozoic. I think that is now set in stone. There are still some discussion about precession obliquity, that's for sure. There are still some open questions in terms of very specific phase relationships between, for example, hyperthermals and astronomical forcing. But to answer your question, no, I think the community now accepts that the Mesozoic-Cenozoic boundary occurs in cycle 164.
Okay, and now I'm going the other way. You show 3 cycles here on which we have good geological evidence. How far does this sequence go when we consider firm ground?
You mean the Zumaya?
Not necessarily, but connected to other part somewhere else. I mean, identification of the 400,000-year cycle somewhere in the world in a continuous sequence from the KT boundary to the past. How far does it go in a continuous way?
I think Linda wants to say that, answer that.
Linda?
Well, the Sonliao Basin in China has a continental equivalent to this particular section that has 400,000 year cycles, and it has in situ geochronology as well. So that section goes all the way into the earliest Paleogene, continues through the down through the upper Cretaceous, all the way down to the Santonian, at least. And that's continuous. So that was published in 2014 by the Chinese, Wu et al. So nobody has looked at whether or not they actually agree.
Yeah.
I haven't looked at it either.
Yes.
These are things that are easy to do. We could get, you know, students in classes to go get the data and do it.
Yeah.
You know. Anyway, so just a comment.
Yeah, that would be interesting to know how far the you see the firm ground goes.
Yeah, and that's an exercise indeed that has not yet been done, and it will really be like how deep can we go, and I'm as optimistic as Linda. We probably can cover most of the late Cretaceous. Maybe we even reach, with Mathieu Martinez on board, the early Cretaceous. Yeah, who knows?
So just to comment, I think one of the challenges is still in the Campanian. If you look at marine sections, there is a bit of not a gap, but there are not so many Campanian very nice records for the marine record. For example, to compare with the continental ones. I think the Maastrichtian is slowly getting resolved. I think Thomas also made a new composite section based on IODP stuff, but yeah, I agree. Slowly we'll get there. It's just a matter of the records and manpower. Yeah.
Okay. Any other question? Late question? Someone who had time to think of one thing. Okay. So thanks again, David, and I hope this time I will be able to put it relatively rapidly online, and we'll be looking for the next talk